Hello everyone! I'm here with a rather different video today, where we're going to use Sage to actually do some of the things we've talked about with at least modestly large numbers. You'll need to be able to use Sage yourself when it comes time to do some of the homework, so I'm going to show you how it works, and I'm also going to go over some of the things we've learned and talk about them and show you what I mean when I talk about things being fast or not fast, or what have you, as we go through these things. So I'm going to go over a bunch of the commands, although, as always, you can look up the commands if you're not sure. So to start with, you're going to want to log in to CoCalc. And so if you don't yet have a CoCalc account, you'll go to CoCalc.com and you'll register for an account, and you'll want to be sure you use your Luther account. By the time you're seeing this video, there will be instructions on how to join the Sage project for this course once you've created your CoCalc account. So when you log into CoCalc, you're going to find you have a blank collection of things once you have chosen the appropriate project. You'll want to go ahead and create a new file for yourself. So I will go ahead and call this one 361 stuff. And the way you tell CoCalc that the thing you're looking for is a Sage worksheet is that you type .sagews, or if you want, you can click down here to say, hey, I want it to be a Sage worksheet. Either way, you'll do that. It'll make it, and you'll find yourself at this blank spot here where you have this whole world in which to do things. Now, the way this works is that if you want to do some calculation, like 2 to the 10th, you can type 2 to the 10th into the window, and then when you hit Enter, it will give you a new line. When you hit Shift Enter, it will actually evaluate it. So you see here it has told me that 2 to the 10th is 1,024, but if I wanted to modify that and have it also tell me 3 to the 5th, then I could press Enter there and have it also tell me 10 factorial. I can have it do that like that. And it'll spit out everything here. Now, I should point out that ultimately what Sage is a large math project with lots of math stuff in it built on Python. And so almost everything you know from Python from your CS 150 course, if you've taken that already, will carry over to Sage. Now, already though, if you're particularly up on your Python stuff, you might already notice one thing that's different. And that thing that's different is that the caret does the thing that a mathematician would expect a caret to do, namely it raises something to a power. If you are used to using Python, you might be used to having to put a star, but if you do that out of reflex, it will still do the thing you expect. So carets work, I'll tend to use carets, but if you, by force of habit, use star, that's fine. Basically, just before it sends it off to Python, it goes ahead and strips out the carets and replaces them with stars. Now, of course, a lot of the time, you don't actually want to display the answer to a particular calculation. One of the numbers we're going to work with today, for instance, is 1,000,000 factorial. And so if I just type that in, and hit Enter like that, it will happily display for me 1,000,000 factorial. However, it won't actually even display the whole thing because, as you might expect, 1,000,000 factorial is a gigantic number, and I'm not really going to gain anything out of looking at this gigantic number. So I can instead go ahead and shove this into a variable. So I am just going to call this big fact for, well, big factorial. And so now, if I go ahead and evaluate that code, it will just store the value of 1,000,000 factorial in big fact. So one thing that might potentially be confusing if you're used to doing a lot of coding in the command line is that you have all of these little mini environments where you can enter commands. And so I have here 3 different ones already. I have the one where I defined big fact. I have the one where I have evaluated 2 times 5, and the one where I've evaluated 13 times 145. And an important thing to keep in mind is that all of these spaces use the same variable set. So if I define big fact up here, I can refer to it down here. So you don't have to put all of your code in one place if you don't want to. You can go ahead and enter new stuff every time. I tend to like organizing mine, so when I do it, I tend to basically pretend that I'm working with a command line version of this. But for you, you can do whatever you're comfortable with. Just be careful that if you have two variables named x, well, it's only going to use the most recent one. Now, a lot of this course we've been talking about in a rather vague way what calculations are fast and what calculations are slow, and sort of hinting and alluding at sort of like where the cutoff size is in terms of numbers. I'm going to do some examples for you today where we're going to look at 100-digit numbers, 50-digit numbers, and 20-digit numbers, and give you some sense just what's super easy versus what's super hard with these numbers. And I'm constantly going to be referring back here to this big factorial. And if you want to know how long big factorial actually is, you can go ahead and ask for the length of the string version of it, and it will go ahead and happily tell you that big factorial is a 5 million digit number. And so if a calculation ends up being fast with a 5.5 million digit number, well, that's a pretty good start. Now, the very first algorithm we talked about, where we said that it was very fast, was the GCD algorithm, or the extended GCD algorithm. So if you want, I can happily take the GCD of this big factorial number with, and let's just go ahead and make up another number that's about that size. So I'm going to pick 10 to the 5 millionth power plus 7. That's also got about 5 million digits. And let's ask for the GCD. And it will think about it for about that long. And then it will go ahead and tell me, hey, that GCD is 1. And if you want, just to convince you it's not just always spitting back 1, you can change this number around and mess around with it, try a few different combinations, and see where this GCD ends up going. Now, we talked also about the extended Euclidean algorithm, and that's implemented as XGCD. I am not going to do the extended Euclidean algorithm with numbers of this size, not because it won't work. It will be no slower than the calculations I just did, but because I don't want it to spit the output at me of the giant coefficients that I want to put in front of these things. But if you want, you could do something like 1200 and 1729. There's the GCD. There's the XGCD. And so the XGCD is giving you the tuple of things that we're used to out of the extended Euclidean algorithm. The GCD is 1. And then if I multiply 1200 by 621 and 1729 by minus 431 and add those together, I get 1. For the rest of today, I'm just going to use the regular GCD instead of the extended GCD, but just remember, it's there and it's not any slower computationally. One thing that has been important to almost every sort of cryptographic system we've talked about, and indeed is important to almost every cryptographic system, is the ability to produce a very large prime number. So for purposes of this, by very large, I'm going to look for a prime number that's about 100 digits. Now, before I think too hard about whether a number is prime, the first thing I want to do is just immediately reject any numbers with a small prime factor. And there's a great way to identify numbers with a small prime factor, namely those which have a GCD greater than 1 with my big factorial here. So I'm going to look for, again, something in the vicinity of 100-digit prime. So I'm going to start at 10 to the 100th. I'll start at 10 to the 100th plus 1. And so when you see that the GCD of big fact and 10 to the 100th plus 1 is this number, it doesn't even matter what this number is, I already know that 10 to the 100th plus 1 is not prime, because this is a factor of it. So I could then go on to plus 3. I'm going ahead and skipping plus 2 because I know that number will be even. Plus 5, plus 7. And so as I go through these numbers, when I'm looking for a number that's a candidate to be a real honest prime, what I'm hoping to find is a number where this GCD is 1. Now, I promise I'm not going to make you watch me type all of these numbers in here one at a time. So what I'm going to do is instead, I'm going to write a for loop. So what have I done here? I've said, take all the values between 10 to the 100th, which is 1 followed by 100 zeros, and 10 to the 100th plus 100, which would be 10 followed by a bunch of zeros and then ending in 100. So I'm taking each of those numbers, and I'm calculating their GCD with my giant factorial. Only when that GCD is 1 am I going ahead and spitting that number out on the screen. And so you can see from the output here that there are 2 candidates for numbers that might be prime in this 100-digit range. So to see if this worked, I'm going to go ahead and try the factor command on these numbers. So I'm just going to copy-paste this first number here into the factor command and wait for Sage to spit out the factorization of this number. And once I see this, I realize, okay, well, my number is not prime. But if you remember what we did, I didn't really look for numbers that had to be prime. I'm so far just looking for numbers that have no small prime factors. And this is, as it would happen, a number that has no small prime factors. It just has lots of medium prime factors. So let's do the same thing for the next number. And already you might be seeing this thing I've alluded to in class, that factoring large numbers is hard. We got lucky in the previous number, that the previous number we were able to pick off the factors. Here we're not so lucky. If this goes on for long enough, you'll see this process button turn red, you'll see this giant yield sign up here, and basically what that's telling you is that you've outstayed your welcome in terms of the server. So this command is taking up lots and lots of server memory and lots of their power, and so it's basically cutting you off. And so at that point, you have to go ahead and hit stop and just accept that you're not going to get Sage to factor this number for you. This number is too large for Sage to factor. Now, just slight proviso, for whatever reason, Sage does not have the best factorization algorithm implemented. It has a pretty good general purpose factorization algorithm, but if you specifically wanted to factor this number, you could go ahead and find the best factorization algorithm out there, and it will go ahead and give you a factorization of this number, probably in under an hour. Interestingly, at least last I saw, the best factorization program for general numbers that I was aware of was run by some grad student out of Ireland, who presumably isn't a grad student anymore. Now, if you think about it, the thing I wanted to know about this number wasn't really its factorization at all. The thing I wanted to know was whether it's prime. And so instead of using the factor command, if the thing that you want to know is whether your number is prime, you should use the isPrime command instead. And you will see that unlike the factor command, where we crashed the server, the isPrime command immediately spits out false. This number is not prime. Now, we'll come back to exactly how Sage knows this number is not prime, and how we know this number is not prime in a moment. But for now, I'm going to go ahead and just save this number so that we'll have it for later. And I'll go ahead and call this fake P, because this number looked kind of prime, but then it turned out not to be. Before we run too much further down talking about these giant numbers and trying to find a giant prime, I want to talk about how Sage implements modular arithmetic. And what you might be used to doing for modular arithmetic if you've done much coding is this. And Sage will absolutely respect that, but you should never ever use this in Sage. And the reason why you shouldn't use this in Sage is that Sage is not doing anything smart when you ask it to do modular arithmetic in this fashion. Indeed, what Sage is doing in this instance is it's just computing 2 to the 8th, then dividing it by 17 and spitting out the remainder. And so as a result, none of our nuanced ideas about modular arithmetic are being taken into account here. Instead, if you want to do modular arithmetic, you should tell it that that's what you're doing. And so if you want to work with the number 2 mod 17, you should write it in this fashion, big M OD of 217. So this is the entity known as 2 mod 17. And so if you now want to raise this to the 5th power, it will let you do that. If you want to take its inverse, it will let you do that. Now, we've sort of implied that modular arithmetic is an okay thing to do, so hopefully this won't take too long. Let's go ahead and just see if we can take our giant factorial, which remember is about 5.5 million digits. Let's see if we can mod that by our 100-ish digit prime, see if that works out okay. That seems to have worked out fine. It gave us this immediately. And so this is giving me this giant remainder. And note, it calculates that in a split second. That's no problem, even for numbers of this enormous size. Another thing we talked about with modular arithmetic was inverses. And so you'll see that if you ask for the inverse of this thing, it will also spit that out right for you. Now, you actually kind of already knew that that was going to work because I showed you the xgcd function earlier and how quick that was, and remember that calculating modular inverses just comes from that extended Euclidean algorithm. But again, even working mod a huge prime, or in this case, not prime, calculating the inverse is no problem. Another thing we talked about was this repeated squaring algorithm for calculating large powers. So we can go ahead and pick your favorite large power, and we can calculate this. And you'll note in the blink of an eye, it calculates this. And even if I keep hitting 0 here for a really long time, it still calculates it in a blink of an eye. This is because as soon as you put something in these mod parentheses like this, Sage knows it's supposed to use the fast repeated squaring algorithm for modular arithmetic. Now, here is the thing you should not do. Because if you do this, at the point when Sage is evaluating this, Sage has not actually been asked to think about this as a modular thing. What this is asking Sage to do is take the, quadrillionth or so power of a million factorial, and then after taking that gigantic power, go ahead and mod it by our fake prime. And that is not something that you can use repeated squaring for. In fact, that is going to involve calculating this quadrillionth power of a million factorial, and that is not going to be pleasant at all. Now, fortunately, Sage has a thing to catch you if you try to do this. Namely, if you put a giant power in a mod and you put it in the wrong place, Sage will throw an error at you instead of evaluating it, which is very nice because if it actually tried to evaluate it, it would take until the end of time. But again, as long as you put the power outside the mod thing, then it will know, okay, I am doing this thing where I can use my best algorithm for everything involving modular arithmetic, and it will do that for you automatically. You don't have to tell it to use the repeated squaring algorithm or anything like that. Now, you might remember that there's a particularly interesting power to take something to if I'm looking mod a number to see if that number is prime. Namely, we have this power. So I want to know if fake p is prime or not. Sage already told me it's not, but I'd like to see for myself that it's not. And so one way we have learned to look for prime numbers or look for non-prime numbers is to raise them to this p minus first power. And so I took just this random base, which happened to be a million factorial, but it doesn't matter. And I raised it to the fake p minus first power mod fake p. And now I want you to remember, if this were a genuine prime, then when I did this, what would happen? Well, this gigantic remainder would have to be 1. That is what Fermat's little theorem says. But this is clearly not 1. And so what that tells me is that, in fact, my fake prime is not a real prime. And so even though Sage was so kind as to tell us that before with its isPrime function, actually we now, even just using the math we've learned in the class, we can already see this number is not prime. Now, I still want to find a big prime. These two numbers just aren't it. But what I'm going to do is I'm going to go back to my little for loop before where I was looking for primes, and I'm going to go ahead and add in a second test. Namely, I'm going to actually input the Fermat test here. And so I'm going to go ahead and do the Fermat test on those numbers that pass the first test. And I'll go ahead and look at what does the Fermat test with the base of 2 tell me. And I'll have it go ahead and tell me, okay, if it passes the Fermat test to base 2, that tells me the number's probably prime. If it fails the Fermat test to base 2, I'll have it tell me that. And remember, what that tells me is n is definitely composite. Now here, I just ran through the two cases that we already saw. Both of those we knew were not actually prime, and in fact, the Fermat test picked up on both of those immediately. I can go ahead and extend this out a little bit, have it look for more numbers. And you can see, actually, if I look at now the first 1,000 numbers after 10 to the 100th, I actually stumble upon two numbers that pass the Fermat test. So there's that one and that one. So let's grab this number. And let's be optimistic, and let's go ahead and call that number P. So this is a 101-digit number that I think is probably prime. And why do I think it's prime? I think it's prime because I did the Fermat test on it to base 2, and I saw that if I did that, I got 1. That's what my for loop before did. But if I want to do my due diligence here, I shouldn't just do the Fermat test to base 2. I can also do the Fermat test to base 3. And I can also do the Fermat test to base 5. And base 7. And once I've done all of those things, I now have done 4 different Fermat tests, unless I'm so unlucky that this number happens to have been a Carmichael number, which is far less likely than winning the lottery, then this is a genuine prime. Now, in fact, actually, Sage implements a deterministic primality test. So that is, Sage will actually tell you if this number is really prime or not if you ask nicely. And you'll see that, in fact, this number actually is prime. So we can go ahead and do all of our fun primey things with this number. So here we have a 101-digit prime. Again, I want to emphasize, up until I put this in, everything we had done so far was all stuff we could do purely with the math we'd done in class. Repeated squaring, the Fermat test, all of that kind of thing, to get to the fact that this number is almost certainly prime. I'm going to go ahead and call 7 mod this number x, just so that I can refer to it. And I want to note that x still knows it is mod this number. So if I do anything with x, like if I do x times and I multiply it by my big factorial, I will still get back a number here, which is mod this number p, my 101-digit prime. I know that because, remember, big fact is a 5.5 million digit number, and this is definitely not a 5.5 million digit number that I got back here. So again, this mod command is doing something very different than the % command that you might be used to, because it is permanently marking this thing as existing in the mod p universe. And so every operation you ask to do on x from now until the end of time, it is going to do mod p. Now, if you want to perform a calculation on something, like for example x, you do that by calling one of the functions that x knows about itself. And those functions are accessed by putting a dot there to say, okay, do this thing. Now, one really nice feature of this Sage terminal is that there's tab completion. And so x, remember, is 7 mod p, and I want to know what things I could do to that. And so often there's a particular thing I want to do, and I just don't know what the command for it is called. But fortunately, if you put the period and then push tab, it will give you this big list of things that Sage knows how to do with it. Now, lots of these are things that you probably don't want. Now, some of them are things you want. So, for example, the isPrimitiveRoot function. We know what it means to be a primitive root. And if you go ahead and type x.isPrimitiveRoot, Sage will go ahead and happily tell you, no, this number is not a primitive root. What else shows up that we recognize? Well, is_square is there right next to isPrimitiveRoot. So we could ask, hey, is this number a square, mod p? And Sage will in fact happily tell us, yes, this number is a square. Now, I should point out, this is telling you, without explicitly telling you, that Sage knows how to decide if something is a square in a way that's smarter than any of the ways we've talked about so far. Because so far, all of the ways we've figured out if something is a square have involved squaring every element of the mod p universe. Because of the size of this number, I know that in that split second that went by, Sage definitely did not square every number in the mod p universe. Sage did something else. And we'll talk about what that something else that Sage did is later. It turns out that there is this very powerful tool called quadratic reciprocity that allows you to calculate whether numbers are squares or not without actually having to decide what it's the square of. Now, another function that might jump out at you, closely related to is_square, is the function square root, because we've done a lot of calculating square roots, but all of the ways we've calculated square roots have been an enormous pain. And so you might say, okay, hey Sage, do you know the square root of 7 mod this prime? And here we see Sage has dutifully provided us with our square root. If you want to check that Sage is really right, because maybe you don't believe it, you can go ahead and check that actually if you square this number mod r prime, you really get 7. Now, if you noticed, that really went by in the blink of an eye. If you want to know how long a command is actually taking, you can use this command called timeIt. You then have to put this thing in single quotes. And then Sage will do a bunch of iterations of doing this, and it will tell you the average. So it's telling you here that it did this 625 times, and the average amount of time it took Sage to calculate the square root modulo this number of 7 was about 27 microseconds. Now, one of the first things we checked was whether 7 was a primitive root, mod p. And it turned out that 7 was not a primitive root mod p. So we might say, okay, well, how do you find a primitive root mod p? Well, that you do with the primitive root command. And so if you type, for example, primitive root 7, it will tell you that 3 is a primitive root mod 7. If you go ahead and type primitive root p, then Sage will go ahead and it will think for a while. Now, actually, if you remember the algorithm that we described in class for finding primitive roots, that algorithm relied on factoring p minus 1. And, well, we've already seen previously that we can't factor a generic 101-digit number in the split second that a lot of these calculations are going by in. And so what's happening here, the reason why Sage is doing its whole red chip business again, is that it's trying to factor this number minus 1, because the algorithm we talked about is basically the best one for finding primitive elements. And Sage is basically using up all the memory that CoCalc will give it, and Sage is not successfully finding the factorization before CoCalc cuts it off. So let's go ahead and scale down our prime. So let's, instead of thinking about a prime that is this large, let's think about a prime that is half as many digits, just so that we can see this stuff work. So we're going to go down to 50 digits, and we'll run the same loop, and we'll spit out some numbers. Let's see. This one, it says, is probably prime. So let's go ahead and let p be this now. Let's actually check that Sage is capable of factoring this number, -1. Sage is capable of factoring this number, -1. And so hopefully that means that we should be able to have Sage give us a primitive root mod this number. And lo and behold, there it is. Because Sage can factor p-1, and it can factor p-1 very quickly, it can find us a primitive root. Note the world of difference between factoring a 50-digit number and factoring a 100-digit number. Any 50-digit number you give Sage, it's going to be able to factor very quickly. But 100-digit numbers are quite often going to bog Sage down quite a bit, as you can see. Now, why did we talk about primitive roots? Well, one of the reasons we talked about primitive roots was so that we could take logarithms. So remember what being a primitive root means. It means that every number mod p other than 0 is a power of this number, which I've now gone ahead and called g. And so it makes sense for any non-zero thing to ask the question, hey, what power of g is this? And so I could ask, for example, g here is 11. What power of g is 121 mod p? And what you will notice is that Sage is not smart enough to figure out that 11 squared is 121. Now, Sage, in fact, actually is smart enough to figure out that the power you have to raise g to in order to get g is 1. So that's something. But Sage doesn't even notice because Sage's discrete logarithm algorithm gets bogged down even for primes in this size. So primes of this size, if you go ahead and try and calculate the discrete log of just some random number here, it will, as you can see, fail. And if you wait long enough, it will red chip on you and all of those kinds of things. This is, again, a good thing rather than a bad thing, because, again, a lot of our security systems rely on the idea that calculating discrete logs is capital H hard. So if it turned out that any of these random things I could go ahead and just calculate a discrete log in Sage in a half a second, that would probably be a problem. Again, just to show you how this works, I'll go ahead and find an even smaller prime, just so that you can see that Sage actually can calculate discrete logs for small enough numbers. So I'll go ahead and go down to p being this. So let's see, can p find us a primitive root? 3 is a primitive root. And so let's try and figure out what power of 3 7 is. And now we're back into the Sage can figure this out almost right away. Sage claims that this is the power. So let's check that. And there you go. So this gigantic number, if you raise 3 to that power, you get 7. Now, again, you can see that Sage must know something that we don't. Because even though Sage utterly failed to do this even mod a 50-digit prime, it certainly succeeded mod this 20-digit prime. And the only way we've so far calculated discrete logarithms is by writing out all the powers. And definitely Sage did not just write out all the powers of 3 until it got to this one to decide, okay, that's the power I need to raise 3 to in order to get 7. So again, and we'll talk about this a little bit later, Sage knows something we don't, that is making this calculation faster for Sage than it would be for us. Now, there's one thing that we've talked about that we sort of wanted to do that we still haven't been able to do. And that is, we want to be able to find a big prime and a primitive root modulo that prime. Now, remember when I took my 100-digit prime and I tried to get Sage to find the primitive root, it did not succeed. And the reason for that was because Sage could not factor that prime minus 1. If I want to actually find a 100-digit prime where I can find a primitive root, what I have to do is specifically look for primes where I'm going to be able to factor p minus 1. So I'm going to go back to my loop here, and I'm going to modify this to try and look for numbers where not only is the number prime, I'm also able to factor it in a reasonable way. I'm also going to go ahead and dump the part where it tells me that the thing failed the Fermat test, so I'm just not going to hear about the things that failed the Fermat test, but that's okay. So I'm here currently, and I've found a number that's probably prime. How do I go ahead and find out if n minus 1 is going to factor nicely? And the answer is, I want to pull out all the obvious factors of n minus 1. Here, when I say obvious, I of course don't mean obvious to us, I mean obvious to Sage. But for example, n minus 1 is certainly even, so you can pull out a 2. But what's really convenient here is that actually we have this giant factorial laying around. Remember, big fact, this is the product of every number from 1 up to 1,000,000. So all the small factors are already in 1,000,000 factorial. So we're going to call the small factors of n minus 1 the smooth part. For whatever reason, whenever computational number theorists are talking about small prime factors, they always use the word smooth. There's not a super clear name for the other part, but I'll just go ahead and call it the rough part. And so the rough part, that is, after I factor out all the small prime factors from n minus 1, what's left, this is going to be n minus 1 divided by the smooth part. And so just to get a sense for what's going on here, let's go ahead and do this for some numbers. Let's go ahead and print the smooth part, followed by the rough part for some of these numbers. So now this loop is going through, and it's only showing me the numbers that it thinks are prime. P minus 1 here is getting split for all of these numbers into two pieces. A smooth part that we've got by grabbing all the factors from 1,000,000 factorial, and a rough part. We definitely know how to factor the smooth part. That's no problem. We can do that just with trial division even, because all of the prime factors of this have to be less than 1,000,000. And so what we're looking for is a place where we know how to factor the rough part. And if you think about it, there's one specific kind of number that is really easy to factor. And that is prime numbers. So the way we're going to find a prime that meets our needs here is to look for a number where the rough part is also prime. So how am I going to do that? I'm going to do that by again invoking the Fermat test. So I'm going to go back, modify my code just a smidge here. So now after I calculate the smooth part and the rough part, I'm going to look and see if I'm lucky enough that the rough part itself I think is prime. And in those instances, I think probably I'm going to be lucky and I'm going to be able to factor n minus 1 where n itself is prime. So let's see what that looks like as the program goes through it. And so you can see already here in this instance, we have found a likely candidate for something where the number is prime, and we'll be able to factor the number minus 1. So let's double check that this is really true, that this is really a number where this number is prime, and this number minus 1 is something Sage can factor. So there's the big number. So we'll ask Sage first, hey, is that number really prime? Sage says yes. And then we'll factor that number minus 1 and cross our fingers that Sage doesn't explode trying to do that. And Sage didn't explode trying to do that. And again, the reason why Sage was able to do this so quickly is that Sage was able to pull off the smooth factors, These things I've highlighted, those are the smooth factors that we pulled out of the GCD with a million factorial. And we just happened to be so lucky that the other giant factor was prime. So the rough part, as we called it, ended up being prime. And so this is an example of a large prime where we can factor that number -1. So if we want to be able to find a primitive root modulo a large prime, we can't just settle for any prime that's large enough. We need a prime that's large enough where we can also factor p-1. But as soon as we have that, you'll notice that if I just ask Sage, hey, what's a primitive root mod this giant prime? And it will tell me 3. 3 is a primitive root. So what can you do with this primitive root? Well, once you have this primitive root mod this large prime, you have everything you need in order to do the Diffie-Hellman key exchange that we've talked about, or in order to use the Elgin-Wall cipher that we've talked about. And so really, once you get here, and once you understand what we've done so far, you can see actually we have now all of the math to at least implement all of those pieces. And again, we've talked about the math behind everything Sage is doing outside of the isPrime command. But we have our own approximate isPrime command just with the Fermat test, and that was good enough for us to dig up these kinds of primes. On the homework, I'll ask you to do some similar calculations in Sage for yourself. And so you'll get to work with some of your own giant primes and some of your own giant factorials, just to practice and get a feel for what these calculations are like, and what things you can do, and what things you can't. And this really sort of remarkably vast chasm where you might notice that basically every calculation we asked Sage today either evaluated in less than a second, or crashed Sage. There was not really a whole lot of gap between those two things. And if we're doing our cryptography stuff right, that's how it should work. Everything we need to do to implement the cryptosystem should be easy. It should be happening almost instantaneously. And anything that would result in us breaking the cryptosystem, like calculating a discrete log or factoring a giant number, those should be impossible. That's all for this video. I will still post a chapter summary, although this goes over a lot of the stuff from the chapter, but I'll post that later. But I'll wrap up here for now. Have a great afternoon.